Hello and welcome to lecture 33. So today we're going to talk about area between curves. So what is this about? So, given two functions, f and g on the interval ab, where f of x is greater than or equal to g of x for all x between a and b, then we claim area between curves f and g is given by this expression. Okay, so as always, we draw a picture. And in this case, it's one of the rare instances where there's an explanation in the book that's too complicated. So, if we have our function f, it lives like this, okay? Let's take our function g underneath it, so this is g, this guy's f, okay? And the area between these two things is clearly this red stuff here that I'm sketching out. Yeah, that's the area between the two, yeah? And if we think about the area underneath the graph of f, then what is that? That is all of this stuff here. Yeah? And if we think about the stuff which is the area underneath the curve given by g, it is all this stuff here. Yeah? So, we can clearly see that the red stuff, which is the stuff we're trying to find, right, is equal to the total blue stuff, right, all the stuff underneath the graph of f, minus the total green stuff, the stuff underneath the graph of g. Yeah, we can just see it. Yeah? So, if we express exactly that thought, if we express exactly what we see from the picture in the language of maths, that is that the area we're looking for, area, is equal to, again, the area of this thing, which is all the stuff which is underneath the graph of f, which we know is represented by this definite integral, minus the area underneath the graph of g, which is represented by this integral, which is exactly this thing by properties of integrals, because integrals are basically sums, just more sophisticated sums. So that gives us our expression over here. Yeah? So this is an easily believable true thing, right? This is a true formula. And we can use this to calculate these kind of stuff. And with the formula makes sense, nothing to memorize. It's just clear from the pictures. We can easily answer these kind of questions. So here's our first example. Find the area bounded above by a to the x and below by y of x equals x over the interval (0 to 1). Okay. All right. Solution. We, as always, went over a picture, so I'm emphasizing this a great deal, and it's absolutely essential in this section too. So we have the function e to the x, right? So when x is equal to 0, e to the 0 is just 1, so we're here, right? And then when we're at 1, we have the value e, which is like 2.7, so this is e to the x, say. Yeah? And then we have the function y equals x. So this is not a good picture because the slope should be 1, but this is the function y equals x right here. So there's clearly e to the x is above it, and what we're looking for is this area here, all this stuff. Yeah? And we know what is the mathematical expression that represents this thing. We know in the language of maths how to describe this area. It is exactly given by the integral from 0 to 1 of e to the x minus x dx. We know the antiderivative of this thing. We differentiate e to the x, get e to the x. We differentiate x squared over 2 to get x, and then we just have e to the x minus x squared over 2. And then we just put in the numbers. When x equals 1, we have e to the 1 minus a half. And then when x equals 0, we're going to have e to the 0, which is 1, and this thing will be 0. So then we're going to have just minus 1. So then this thing is just e minus 3 over 2. And a quick reality check. The answer has to be positive because it's an area. E is 2.7 something something, so 2.7 minus 1.5, it's positive. This looks like a reasonable answer, and indeed it's the correct answer. Yeah. So our first example, pretty straightforward. Okay, second thing to learn. We're going to talk about when an area is enclosed by two graphs, which means that the two graphs will define some enclosed area as the intersection of their two graphs. Probably didn't say that well. Okay, better to draw a picture. So if we have a graph like this, and we have a graph like this, then this stuff is the area enclosed by the graph. And when you see these kind of problems, you will only see one area enclosed by the graph. Obviously, it's easy to construct examples where there's many, but you'll just see one. Or maybe you'll see more than one, but then they'll specify which one we're trying to figure out. But most of the time, you'll just see one. Yeah, where this would be, say, F, and this would be G. And we would like to try and calculate this, okay, using what we've learned already. So let's do an example. Example 2. Find the area by y1 of x equals x squared, y2 of x equals 2x minus x squared. Let's write this better. Let's do this better. Like this. And that is our problem. Okay. Solution. Okay. First thing to say is that actually the way the question was phrased in the book, I believe, wasn't like this at all. and it was like this, but it didn't look like this. They wrote something like this. Okay. And when you see something like this, the first thing to do is to give these things different labels. Don't call them both y. That's just a recipe to get confused. So first thing to do is go let y1 equal x squared and y2 equals 2x minus x squared. We can factor in x, and then we're going to have, oops, x of 2 minus x. Yeah. And now we draw a picture. Let's put it over here. So, x squared, we know what that looks like. Again, we have to be fluent with these elementary functions. For sure, you have to know what x squared looks like. That has to come without thinking. This thing, well, since there's a -1 in front of the x squared, we know for large x, it's curling down, right? So it's a quadratic which is curling down somehow. This is factoring it out, so we know actually the roots are going to be 0 and 2. So it's going to curl down and do something like this. Right? Well, this here is 0, and this here is 2. Yeah? Cool. And then it's clear what we're talking about. The enclosed area is this stuff right here. Yeah? And we have just one thing that we know gives us the area, and that's this formula where we integrate f minus g, where f is on top, over some interval where that's true. Yeah? So clearly, what we need now is to find the interval, which on this picture is this thing, from here to here, where that's true, where this function here is on top of the other one. Let's give them labels. So this one is y2, and this one is y1. Yeah? We need to find the interval where y2 is above y1, and then we'll just be integrating y2 minus y1. And that then will give us exactly this area, which we're trying to find. Yeah? Cool. So how do we find this interval? Yeah? Well, it's got to be the x for which y1 of x equals y2 of x, as we see from the picture. Yeah? Yeah? We go from the picture, we're going to express in the language of maths, and we'll do some computations and then find out more details. Huh? So, to find interval, set y1 of x equals y2 of x. If we do this, what happens? We have that x squared equals x2 minus x. Yeah. And obviously x equals 0 is a solution, so let's divide through by x, taking x to be non-zero, looking for the non-zero solution. So that's the same as x is equal to 2 minus x, which implies that 2x is equal to 2, which implies that x equals 1. Therefore, this thing here is at 1. Yeah? So my picture's not very good because this gap is too big, but we know what this is now. So we know exactly the interval. We have to integrate from 0 to 1, and we're going to have to take y2, this guy on top, minus y1. Wonder if I can squeeze that in. Let's try and squeeze that in. Erase some of this other stuff. Okay, so we, from the picture, for sure know that y2 is bigger than y1 over this interval that we're interested in. So we set up the integral, it's from 0 to 1. We're going to put y2 here, which is 2x minus x squared minus y1, which is given by this. And that thing has to be the area, right? So let's write that 0 to 1. Let's take out the 2. We're going to have x minus x squared dx, and then this is Easy to calculate, right? We know the antiderivative, x squared over 2, x to the 3 over 3. Put the numbers in. When x equals 1, we have 1 over 2 minus 1 over 3. 1 over 2 is 3 over 6, right? 1 over 3 is 2 over 6. So it's going to be 1 over 6 times 2, which is just 1 over 3. And that's the answer. That is the answer. Cool. So this thing here, this area is 1 over 3. It's a positive number. That's what we expect. And it looks about right. Yeah? Within the scale of this, 1 over 3 seems like a reasonable answer. And it is the correct answer. Yeah? So it is not particularly difficult to do this. Let's go over the steps. We had our two functions. First thing, we gave them different labels. Do not call them y of x for both of them. Please do not do that. Do not do that. Call one of them y1, one of them y2, or call one y and call the other one z, but not the same name for both of them. Yeah? They're different things. You're just going to get totally confused if you call them the same name. So this is this guy, this is this guy. Yeah? Then we draw a picture of these two different functions. Yeah? We draw the picture, and then we can see that there is an enclosed area, just one. So it's clear what we have to calculate. It's a meaningful thing. We now know what we have to calculate. And knowing what we have to calculate, we now understand that we need to find the interval which this region lives above, because we're going to have to integrate an x over this region, over this interval, sorry. Yeah? So to find this interval which this region lives above, we're going to set y1 equals to y2, because clearly that's going to give us this, and 0 we can see has to be the other endpoint. Yeah? So we do that. Easy bit of algebra. We find x equals 1. Good. Now we've defined these endpoints of the interval. We set up the integral from 0 to 1. And then the only thing remaining to get right is to have the bigger guy on top. And the bigger guy from our picture is y2. So we put y2 here. Let's color coordinate this. This guy is this guy. Yeah. Minus y1. This guy and this guy. Yeah. Then we just carry out the integral. From this point onwards, it's just doing a standard integration, right? So it's all stuff you know how to do, yeah? Based on what we've learned already. So the new stuff is reading this thing, translating it into a picture, reading off from the picture what we have to do, finding out the interval we have to integrate over, and then just doing the integration. Yeah? Cool. All right, so I'll erase the board, and then we'll talk about something a bit more subtle. Okay, so now we're going to talk about the area between two curves where one is not strictly above the other. So given f and g defined on the interval a to b, then the area between f and g is given by a to b, the absolute value okay, so as always, it's going to make sense to us with the picture. So this is A, and this is B, and now we have just two arbitrary functions, f and g, where it's not necessarily the case that f is bigger than g throughout A to B, and vice versa. So let's draw f, which does something like this. This is f. And let's draw g that does something like this. This is g. Okay. I want them sticking up like this. F and G. Okay, so if f was bigger than g, then this formula would be just the same as f minus g, yeah? And it would be exactly the formula we've already discussed and we already believe, yeah? So that is fine. Then we believe it, yeah? If g was bigger than f, yeah, then this thing would be the same as g minus f, right? And again, this thing would be something we believe because it comes down to the formula we've already agreed on, yeah? So in those two cases where either f is always bigger than g between a and b, or vice versa, g is always bigger than a, g is always bigger than f from a to b, in that case, that for sure gives the right formula. Yeah? But now we're looking at this thing where it's not necessarily the case that, that one is bigger than the other throughout the entire thing. But the area we're trying to understand is clear, right? We are trying to understand this stuff here. We're trying to understand this area here, which I'm sketching out. That's our mission. Our mission is to understand why this thing, yeah, is in the language of maths described by this thing. Yeah? Cool. Now, the best thing to do would be for you to stop the video with this and just ask yourself that question. Try and figure out why this thing is the reasonable expression in the language of maths, or the correct expression language of maths of this thing. Yeah? Yeah? And I claim if you do that and you think about it for long enough, you will see it. And that's by far the best way to proceed. Huh? So give that a go, give it a good shot, try and think undistractedly for 10 minutes about this. And if you're completely stuck and you're having no ideas, then press play. Otherwise, give it 10 minutes, see if you come up with some kind of answer before you see me show you why that's the case. Cool. All right, so why is that the case? Well, as I said, it's definitely true when f is bigger than g, and it's definitely true when g is bigger than f. Yeah? Someone in class today pointed out that this reminded her of the formula for total distance traveled compared to the formula for displacement. And indeed, there's quite a parallel there. Yeah? And then we're also going to understand it in quite a similar way. Because if we look at this thing here, then we can cut things up into these different pieces. And that's part of the reason I'm doing this, because that's how we're going to learn to solve these questions going forward. The reason why this is true is also the method we're going to use to solve these questions. Yeah? We cut them up like this. Let's call this thing C, and let's call this thing D. Yeah? So from A to C, we have that F is bigger than G. Yeah? And then from C to D, we have that G is bigger than F, and then from D to B, F is bigger than G. Yeah? So if we break this thing up and then talk about the areas of each individual piece, so let's call this part here capital A. Yeah? Let's call this thing here capital B. And by that, I mean capital A is this area, capital B is this area, and capital C is this area. Yeah? Then understanding the area of capital A, yeah? Well, let's say that better, understanding what capital A is, since we agree capital A is the area, yeah? We know how to do that because that's the situation we already understand, where one guy is on top of the other, where in this case F is above G. Yeah? So we know that A is integral from A to C of f of x minus g of x dx, right? Because f is bigger than g. Yeah? And since f is bigger than g, this is the same as this. Yeah? Cool. And we know that b is going to be the integral from c to d. And we're going to write here g of x minus f of x, because g is bigger than f. Yeah? But if we think about that, that is exactly the same as the integral from c to d of f of x minus g of x. Yeah? Because since g is always bigger than f over this interval, yeah? then this quantity is the same as the absolute value of f minus g. Yeah? Just true. And then let's do from d to b, same argument, pretty much, that this thing, c, is equal to the integral from d to b, f of x minus g of x. But again, since f is bigger than g in this interval, this is the same as this. Yep. So the total area, so area between graphs, is given by a plus b plus c. Yeah. And then we just put down the expressions here. So we have, in the language of maths, expressed what a, b, and c are. So this is the integral from a to c, f of x minus g of x, dx, plus the integral from c to d, f of x, minus g of x, plus the integral from d to b. Yeah? And then what's this? Well, we already know that if we have some interval like this, let's say, running out of letters, let's say this is a1, and this is a2, and this is a3, and we have some function, whatever, defined from a1 to a3, then the integral from a1 to a2, let's call this function h, or h of x dx, plus the integral from a2 to a3, h of x dx, is indeed equal to the integral from a1 to a3, h of x dx. Yeah? Basic properties of integrals we already discussed. Huh? And that's all we're using here. So we have broken the interval a to b into interval from a to c, then c to d, then d to b. Yeah? All of the same function throughout. So that thing is just equal to the integral from a to b of exactly our expression. So we believe our expression. This is mathematically the way in the language of math to describe this thing. Yeah? Yeah? Cool. All right, so with this, we can answer this kind of question. And that's our next example. Find the area between over 0 to pi over 2. Okay, solution. Of course, we're going to draw a picture. 0, pi over 2. So we know what cosine looks like. Comes down like this, it's 0. This is cosine. And we know what sine looks like, right? This is what sine looks like. Yeah? Cool. So, what area are we trying to find? Is this stuff. Easy enough. Yeah? So, by the way we've understood this formula, we know that we can calculate this by breaking it up into pieces, right? piece where the cosine is bigger than the sine, and then a piece where the sine is bigger than the cosine. Yeah? To do that, we need to find what this point here is where they exactly cross. Yeah? Where, in other words, cosine is equal to sine. Yeah? So, solution. Need to find the intervals where y1 is bigger than y2 and y2 is bigger than y1. Yeah? So set y1 of x equals y2 of x, which is the same as insisting that sine of x equals cosine of x, which is the same as tan of x equals 1. Yeah? Okay, let's draw a picture. And let's create a right-angled triangle like this. Okay, so if this angle here is x, yeah, and tan of x equals 1, well, we remember from when we first learned trig, right, that tan is just the opposite side divided by the adjacent side, yeah? So it means that the opposite side divided by the adjacent side is equal to 1. In other words, these things have exactly the same length, yeah? So we might as well just give them length 1. So this is length 1 here, and this is length 1 here. Yeah? Cool. So we ask ourselves, what angle can we have such that this length is the same as this length? Should be clear to you. That's 45 degrees. That's pi over 4. Yeah? So then x. And some of you might have some numeric, whatever, mnemonic way to memorize this. Trying to avoid you guys or you people memorizing things. I want you to have pictures to work it out. Huh? And it's not easy to, it's not hard to work out what x has to be if tan of x equals 1. It's just a picture, and we'll see later that's going to help us for some other pieces. Huh? Cool. So we know what this thing is, and we check back with the picture to see if that's believable. And indeed, it's very believable because this looks like a very symmetric picture. Yeah. So it looks like they're crossing exactly in the center of pi over 4, and that's what our calculation said. So it's this backwards and forwards, this kind of dance backwards and forwards from the picture to the language, doing some calculations in the language, checking back on the picture, seeing that everything is consistent, making sense. That's what we're learning to do here. Yeah. All right, cool. So x is pi over 4. We're feeling good. Now we can set up the integral. So we're going to integrate from 0 to pi over 4, and we're going to have cosine minus sine for this region, and then from pi over 4 to pi over 2, and then we're going to have sine minus cosine. Yep. So area equals integral from 0 pi over 4, this thing, cosine of x minus sine of x dx, and then plus the integral from pi over 4 to pi over 2, the other thing, sine of x minus cosine of x dx. Yeah? Cool, we're running out of space. We're running out of space. Okay, let's erase a little bit of this board and then put the stuff on top somewhere. Okay. All right, so this is where we are, right? And at this point, it is just doing the calculation. Yeah? So area equals, and now we're going to put this directly like this. I think this is too far down, too far up. Getting perfectionistic about what I put on this board. Probably not worth it. Okay, let's do it. All right, so 0 to pi over 4. Antiderivative of cosine. We have to think about this. So if we differentiate sine, we get cosine. Yeah? Because sine is the good. Yeah? Just have sine of x. Antiderivative of cosine. If we differentiate cosine, we get minus sine. Yeah? Which is actually the sign that we want. So we just put cosine of x right here. Differentiating this, give a quick check. It does indeed give this. Yeah? And then the next part. Pi over 4, pi over 2. Yeah, okay. Antiderivative of sine, it's minus cosine. Cosine is the bad. When we differentiate, it introduces a minus sign, so we have that minus cosine. And then antiderivative of cosine is sine, so we're just going to have minus sine right here. Yeah. And then we put the numbers in, right? So we have to think about what sine of pi over 4 is. Yeah? But if we look at this picture, this angle we've established is pi over 4. Yeah? So this angle is pi over 4. We know our basic trick, right? We know that sine is going to be the opposite divided by the hypotenuse. So from this side and this side, we know the hypotenuse is this side squared plus this side squared, square rooted. So we have this side is square root of 2. Huh? Cool. So sine of pi over 4 has got to be 1 over root 2. And for the same reason, cosine of pi over 4. Just the adjacent divided by hypotenuse, again, 1 over root 2. So this thing here is going to be 1 over root 2 plus 1 over root 2. 1 over square root of 2 plus 1 over square root of 2. And then minus what happens when we stick 0 inside here. So sine of 0 is 0, cosine of 0 is 1. Yeah? Cool. All right. This thing here, I don't like the minus. Let's take it out straight away. And then let's do things step by step. Let's rewrite this thing. And now we have cosine of x plus sine of x. We've taken out the minus. Now we put in the numbers. When we put pi over 2 inside cosine, we're going to get 0. Put it inside sine, we're going to get 1. So this thing will be, this thing we can simplify. So this will be 2 over root 2, which is just going to be root 2. So this will be root 2 minus 1 minus, and then we put this stuff, pi over 2 into this. Again, cosine will give us 0. This will give us 1. So we're going to have 1 minus, and then when we put pi over 4, we've already found out that this thing here, cosine of pi over 4 is 1 over root 2, and the same for this thing. So minus 2 over root 2, yeah, which is root 2 minus 1. And then this thing is just root 2 itself, right? 2 over root 2 is just root 2. And then so this just becomes root 2 minus 1. And that makes sense, right? Because this part here was when we calculated this part here. And this part here is this part here. And from the picture, that's incredibly symmetrical. It looks like this area should be the same as this area. Yeah? And that is what we found out from this calculation. So we're confident that everything is fitting together, everything's consistent. The dance between the picture and the calculation is working out well. And then the answer is 2 square root of 2 minus 1. And that's it. Cool. So, not too hard, huh? Let's go over the steps. So, we have our function, yeah? I think, again, in the book, they just called it y in both cases straight away. We want to call it y1 and y2. Yeah? And then we want to find the area between the curves. Well, firstly, we draw the picture. Yeah? we have some idea what they're talking about is this blue stuff here. Yeah? And then we want to break up the interval into the parts where one guy is above the other, and then another interval where the other guy is above the other guy. Right? So the interval into where cosine is above sine, and then when sine is above cosine. Yeah? These are two different intervals. So to do that, we have to find the point where they cross. That will define each one of the endpoints. That'll be used to define each of these. That will be used to define each of these intervals. Yeah. So we set y1 equals y2. We solve this, use the triangle, we have pi over 4. So this guy's pi over 4. We check with the picture that sign's believable. And then we write down the expression for the area. Yeah? And it is the integral from 0 to pi over 4, the top guy minus the bottom guy, cosine minus sine. There we go. And then from pi over 4 to pi over 2, the top guy, sine minus the bottom guy, cosine. This guy, all good. Yeah? From this point, it's just calculation. Yeah? Now it is just stuff you know. We know the antiderivative, we put in the numbers, we check along the way that everything is consistent, and we get the answer, and we're good. Huh? Main new thing to learn is drawing the picture and then breaking it up into the parts where one function is above the other, and then where the other function is above the other. All right, good. We have one more thing to do, one more example, and let's do that after I clean the board. Okay, so final topic. Sometimes we want to find the area between two curves that are defined from the y-axis. Yeah? So if we have things defined from the y-axis, it's exactly the same game, right? So if we have this function and then some other function like this, say something like this, and we are doing it from, say, here to here, then it's going to be this area, and this area. And we're just going to integrate, right? We're going to go from A to B, like this, integrating in the y-axis. That's it. So, what do we have to do with this? It's exactly the same game. We're just going to have to do the integration in y. And that means visualizing, drawing things with respect to the y-axis. But it isn't, it's a change, but it shouldn't be anything too difficult. It shouldn't be, I mean, it's morally the same thing. We're just looking at it from a different angle. We're looking at it from the side as opposed to looking up and down. Huh? So, what is perhaps a little bit tricky is to identify when we want to do that. And this is a kind of classic example. Example 5. So find the area. Enclosed by y of x. Okay, I'm going to do it the way they do it, just to give you a kind of a simulation of what you will face, perhaps. So, like this and this. Okay, so I mean, we're used to writing functions from the x-axis, so you might be tempted to define y1 and y2. y1 this one and y2 this one. Yeah. So defining y1 in terms of x is easy in this case. I mean, it's given to us. Here we'd have to take the square root, and then we'd have to think, because the square root of a number has a plus and a minus answer, right? So to actually get the full picture here, we'd have to consider actually two functions, one where it's the plus and one where it's a minus. So then we'd have three functions overall. The whole thing starts to be a bit more complicated. Yeah. So what you should be ready for is that if you try and do that, write functions from the y-axis, write functions from the x-axis, and you can't easily do it, you end up with three functions, then there should be a better way, an easier way, and that is to write them from the y-axis. Instead of writing y as a function of x, we're going to write x as a function of y. Huh? So this is the first curve, and this is the second curve. So do the following thing. Give them different labels first of all. So we're going to write y, and then write them. y1, x1 of y. It's a function of the y-axis minus 1. That's our first curve, and our second curve, y squared, is 2 x2 of y, x plus 6, like this. Yeah? Then we can clean that stuff up, right? Then we can have that x1 of y is equal to y plus 1. And do this in steps if you want to, but I guess I'm getting tired. This is a function of y like this. And then this thing, what is it? If we clean it up, put the 6 on the other side, divide by 2, it's going to be y squared over 2 minus 3. No? Cool. All right. Now, let us draw the pictures, of course. So, look at this guy. So, when y equals 0, this thing is at 1, right? And its slope is 1, right? So, it's just going to be increasing upwards like this. Yeah? So, that is x1. This guy is like this. So, what does it look like? This is just a quadratic curving like this, right? So maybe this is too far away. Let's put the minus 3 like this. And then what do we have? We have something like this. And like this, yeah? And then it's clear what area we are talking about. It's this area. Okay, cool. And then we're in the same territory as before. We need to find out the interval we're going to integrate over. So, oh, damn it. So it should be from here, and then from here, right? From here and here. Yeah? And then we just have to find those points. Huh? So these points happen when, so it's a very bad positioning of x1. Let's put x1 here. This is x1 and this is x2. So this point and this point can be found by setting x1 equals to x2. So x1 of y equals x2 of y. That is the same as y plus 1 equals y squared over 2 minus 3. Yeah? Multiply it through. Minus 6, clean it up. Y squared minus 2y minus 8 equals 0. And then what? Then factor it. Y minus 4, y plus 2. Yeah? Equals 0, which implies y equals 4. And y equals minus 2. And then let's check it out here. That is indeed 4. And that is indeed here minus 2. Yeah? Cool. All right. Then we're in good shape, huh? Then we're going to integrate from minus 2 to minus 4. And we have to get the right guy on top. And we see that x1 is definitely the guy on top. This is x1 over here, right? So it's y plus 1. And then minus the guy underneath. This is the guy underneath. Y squared over 2 minus 3 dy. And then let's just rewrite this like this. Minus y squared over 2. And then we just have plus y, and then we have 4 minus 3, which is just 4. right? 1 minus minus 3. So it's this thing. Then we just do the calculation. So 4 minus 2. Let's find the antiderivative. Let's pull out this minus a half. And then we're going to have y to the 3 over 3, like this, plus y squared over 2, plus 4y. And then we can put the numbers in, right? So this thing is like 4 to the 3, and then this is like minus a 6, or minus 6, yeah? And then this thing is like 16 over 2, and this thing is like 8, yeah? Cool. And then this thing is like 8, like this, and then minus, right? Minus 1 over 8. Yeah, so what is 4 to the 3? It's 16 times 4, 64. Yeah, so actually let's just put in the answer. So putting in the answer directly, we just get that this is equal to 18. And that's it. Cool. All right, so it's the same game as before, except we just had to think of it from the y-axis, and we had to remember, or not remember, but it had to occur to us at this point that we're not going to try and do this as a function of the x. Yeah? We're not going to try and write y1 of x, y2 of x. We're going to think, okay, x1 of y and x2 of y. And we came to that because if we did try and write this as a function of the x, we'd have a problem because this thing would have to take the square roots, and then there's a positive and negative answer. So what would happen is that if we tried to do that, we'd have to have a y1, or if we tried to call this thing y2, we'd have to have a y2 and a y3. And the y2 would be, say, the positive part of the square root, which would give us this part, and the y3 would be the negative part of the square root, which would give us this part. Yeah? So we'd have 3 functions, and we'd have to try and understand the area enclosed by 3 functions. And that isn't so easy. I mean, we could do it, but we'd have to think harder about it. Yeah? And then we'd have to break things up in a different way. We'd have to break them up like this. Yeah? And then we'd have to break them up from there onwards. And this would be the difference between y2 and y3, and this is the difference between y2 and y1. And it just is overall, it's harder. I mean, you can do it, but better to do it all from the y-axis. It's a much neater function. These are much nicer functions to deal with. So that's the main additional thought you need in this kind of problem. But okay, this should be a fairly straightforward thing. This is a section which is basically giving you some kind of a use for the integration techniques that you've used already. We can calculate these specific quantities using our integration tools, and that's the main purpose of this. It should be a fairly straightforward section. Yeah? So practice this. Shouldn't have too much difficulty with it. And if you do, remember my office hours. All right. Have a great day.